for you. I'm fine. I came to say condolences.
Thank you, I appreciate it.
Have you recovered since then?
Yeah, I think I've gotten over it. You know, there's always next year.
Good.
Yeah. Also, I checked the decisions on SCOTUS blog the other day, and I think you would not be very interested in this week's decisions. They were extremely technical, I would say.
Ah, okay.
But yeah, I appreciate it. But you're talking about divergence entanglement. Thing is an IR. In the interpretation of this stuff. Good.
So are you off this afternoon then?
Tomorrow morning.
Tomorrow morning. I'm enjoying your talks. You know, every 10 years it's good to hear a talk about this stuff. Okay.
I actually gave a talk in the Banks Dine time. I don't remember when it was.
Yeah, that was in 10.
So that
2010.
2010. Yeah. So that was, I think you heard it then.
Yeah, so that was only 5 years. Okay,
5 years.
Yeah.
Well, the stuff today would be different.
Yeah, good. No,
well, it's the same.
I have a very different perspective on the audience, but it's kind of interesting to sit there and kind of translate things and then think about all of these dualities. And,
well, I think actually my perspective is closer to yours than that of the audience.
Yeah, because somehow.
Yeah, I'm making analogies with things they never heard about.
The analogies, I'm just sitting there translating, and then I have to think, but he's dealing with supersymmetric gauge theories, which are kind of a foreign thing for a lattice person, and so I have to remember he's got the bosons, who says he's extra. You have these you have these extra hooks.
That's right, exactly right. No, but I was shocked when I said this is how I told the boss of the eta prime, and they never heard about the eta prime. And what?
Why should they? I mean, even lattice people mostly, and lattice students are not. Some of them
really don't know about eta prime. That was a major thing.
I know it absolutely was.
Yeah, it was a real breakthrough.
Yeah.
Is there a place to go to for minor medical things that are recommendations?
So, that's a good question.
Just an insect bite that seems to be infected. I look on the web and they say, go see your doctor.
I would drop into the emergency room of the hospital, but that's because it's right across the street from where I live. I know that there are sort of little clinics around in town, sort of. Okay, so I'll just look them up. What you want to check? There was nothing that you could use in the past. So there's nothing really. I mean, I would call my doctor. I'm a little bit too embedded here. I know that there was.
I'm the same way in Santa Barbara.
Yeah.
I just thought there might be a history of students hurting themselves.
There is, but fortunately it's rare. So everyone is a special case.
Okay, I'll just use Google.
Yeah, look around. I mean, there's the old hospital is up on Broadway, about a mile north of here, and they are gradually moving all of their operations out to my neighborhood, which is East on Arapahoe. But I remember that there was some sort of sort of a simple emergency care place sort of across the street from them. And there's a Kaiser place up there too. I mean, you're in California.
It's only the internet has scared me, but it says go see your doctor.
Well, we have kicks. When are we starting, Mr. Director?
We did kind of end late, but we don't need a whole hour.
Here is Nati, all poised and ready to leave.
Is it already? It's not already. Wait, you started.
It's 10 to 11. It's 10 to 11.
Oh my gosh! So we were supposed to start 5 minutes ago?
Yeah, except that you started late. Okay.
Okay.
And everybody was so happy. I mean, why don't you chase everybody in?
I'll chase everybody.
We'll go on chatting here.
Don't do it too explicitly, because maybe they don't want to come. I reached this stage that I could care less whether they come or not. No, when I was young, I wanted everybody to.
Okay,
What's that? Well, people say that I did that long ago.
Okay. Yes. Yeah.
In a way.
No, I was thinking, how would I approach these lattice, these duality things as a latticey person? And as a latticey person, I sort of say, I only understand what I'm doing when I'm close to the Gaussian fixed point. And then
well, the Ising model is a good example.
No, if you can actually do it. I mean, all the cases I know about, you can do it. And
well, if you can do it, you can do it. The surprise is when you cannot, right?
Yeah, but I mean, the analogy would be, say, going from QCD to pions.
Right.
Basically, you can't get there, but you notice all these things.
Everybody's eagerly waiting.
Everybody's eagerly waiting.
Oh, I don't believe a word you say. Are there any questions about the previous lectures? And again, is the speed too high, too low? Am I assuming you know more than you actually know? Or am I assuming that you know less than you actually know? I cannot believe that I assume exactly right for every single one of you. It's a set of measure 0 for many, many people. Okay. I felt that it would be bad to talk only about things which are ancient. So I thought I would devote the last lecture to something which is more modern. Unfortunately, there's still need for a lot of background that, for various reasons, is not being taught. But some of these things that in this background are extremely important in many applications. So what I'll do today is discuss three-dimensional theories. And I'll highlight some of the peculiarities of 3 dimensions that are different than 4 dimensions. But we will see, so we'll learn several things. First, we'll learn about these 3-dimensional theories. Second, we'll learn about some of these peculiarities of field theories in 3 dimensions. And the nice thing at the end, if I get to it, which I'm extremely doubtful, is that we'll see that if you look from afar and you don't get into the technicalities, the 4-dimensional story is not that different than the 3-dimensional story, which is encouraging, although the details and the technicalities are completely different. So why should we be interested in that? As I said yesterday, the first reason it's there. It's field theory with a different number of dimensions. Some might say that it's easier because it's in no dimensions. In fact, I'll show that in some cases it's harder. You can also say that there are many more 3-dimensional interacting field theories than 4-dimensional field theories. I'll explain why. There are more relevant operators. There are more interactions we can turn on that have interesting dynamics. And there might be applications in condensed matter physics. And in fact, some of the ideas of duality, topological field theory that I'll talk about, and so forth, are extremely popular in condensed matter physics. So I'll start by discussing some new elements that exist in 3 dimensions that are not present in 4 dimensions. The first thing is that in 4 dimensions, we had a bound on the number of matter fields that we can have. If we have too many matter fields, the theory is not asymptotically free. And then it's not, strictly speaking, a quantum field theory. It's only an effective theory in the infrared. And therefore, it's not going to do anything exciting at long distance. In 3 dimensions, we don't have such a bound. Every 3-dimensional gauge theory is asymptotically free. In fact, the coupling doesn't even run logarithmically. It runs faster because the gauge coupling constant has a dimension. So there are many more interacting field theories in 3 dimensions than in 4 dimensions. These superconformal field theories, that I had a few of them in my last lecture. In 3 dimensions, there are many more of them. In fact, for any number of flavors and colors, the theory is interacting. This is the typical thing that happens in these theories. Second, we can consider abelian gauge theories. In 4 dimensions, abelian gauge theories do not exhibit interesting dynamics in the infrared. It's associated with the fact that the theory is not asymptotically free. In 3 dimensions, they do. So we can learn a lot of things from abelian gauge theories. And again, this is something that is extremely important for condensed matter physics. They have abelian gauge fields, and they can interact, and they can do all sorts of things. And with abelian gauge theories, we can also have more knobs to turn. We can turn on these Fayet-Iliopoulos terms, which do appear in the first half of Wesson-Bagger. They can be analyzed classically in 4 dimensions. In 3 dimensions, they could affect the dynamics in an interesting way. There are also more coupling constants. I'll discuss them in more detail later. For example, we have a gauge theory. We can turn on a Chern-Simons term. So this is an integer, but it's still a knob we can turn. And as we have more knobs to turn, we can find richer phenomena and also get more diagnostics of known phenomena, because we have another parameter. We take it to extreme values where we can analyze what we're doing and then go back to the point we are really interested in. And related to all that, we can have richest phase structure that we can have in 4 dimensions. So all that is true even without supersymmetry. But with supersymmetry, we have everything that we had in 4 dimensions and more. And the main reason for that is that there are many more terms we can write down that are gauge invariant and Lorentz invariant in 3 dimensions, and they are not Lorentz invariant in 4 dimensions. For example, if we write the term which is a 4-dimensional vector, in 4 dimensions we're not going to add that to the Lagrangian. If we just reduce this term to 3 dimensions, the 4-dimensional vector splits into a 3-dimensional vector and a scalar, and the scalar is another term we can add to the Lagrangian. We'll use that a lot in our discussion. So far, we talked only about the superpotential in 4 dimensions as being a BPS quantity, something that is invariant under half the supersymmetries, but not invariant under the other half. With more supersymmetries, we can have particles that are in small representations. They are annihilated by half the supersymmetries. Operators can be BPS or can be chiral in 4 dimensions. They can also be chiral in 3 dimensions. But particle states cannot be. Related to that, but they can be if we have more supersymmetries. Related to that is that we can have such BPS strings in 4 dimensions. So in 4 dimensions with n equals 1 supersymmetry, we can have BPS, namely annihilated by half the supersymmetries. We cannot have BPS particles, but we can have BPS strings. Let's reduce that to 3 dimensions. So that if something is not BPS, too bad. It's not going to become BPS. But if we have a string which is BPS in 4 dimensions, we can wrap it on the circle as we compactify, and therefore we can find BPS particles in 3 dimensions. So in 3 dimensions, we have a new thing in the spectrum. We have particle excitations that are BPS, and since they're BPS, we can exactly compute their masses. So there are more things that we can compute, and therefore it's getting more fun. Examples of these particles are things known as skyrmions, vortices. They're very popular in condensed matter physics. They have interesting properties. And if the theory is supersymmetric, they can be BPS, and therefore we can analyze them exactly. We'll also see that there are interesting operators that cannot be written in a simple form, in a simple local form in terms of the dynamical fields in the Lagrangian. This thing exists already in 4 dimensions. In 4 dimensions, we can discuss the Wilson line, which is an exponential of the connection, or more mathematically, the holonomy. But there's also a dual object known as the 't Hooft line, which is defined by removing a line out of space-time and specify the singularity of the gauge field near this line. This is the 't Hooft line. In 3 dimensions, we have one more thing. We can take this 4-dimensional 't Hooft line and wrap it on the circle, and it will give us an 't Hooft particle or an 't Hooft local operator in 3 dimensions. So in 3 dimensions, there are local operators. They are the descendants of the 't Hooft line in 4 dimensions. We have such local operators. And in the discussion, we can have more interesting operators we can discuss. They might be chiral, they might be BPS. We might want to understand the dynamics, the dimensions, the correlation functions, and so forth. I'll construct them very explicitly. So let me start with the first term that is new in 3 dimensions, and it has nothing to do with supersymmetry. So we should distinguish what can and what cannot be in a supersymmetric theory. And it comes under the name real mass. This is a terrible name, by the way, but there's nothing I can do about that. So in 4 dimensions, the mass term is complex. I'm using two-component notation. We can write this thing with a complex parameter m, or we can write its complex conjugate, which is m bar, psi bar alpha dot, psi bar alpha dot. I hope you know this notation. So such a mass parameter is always complex. In 3 dimensions, there is one more thing we can do with the fermion. We can write, I'll use the same notation m, psi alpha, psi bar alpha. One way to understand that is that in 3 dimensions, there is no difference between alpha and alpha dot. If I ignore signature and so forth, and the global structure, the Lorentz group in 4 dimensions is SU2 times SU2. So every representation is described in terms of 2 spins for the 2 SU2s. Alpha is a spinor index for one of them, and alpha dot is the spinor index of the other one. In 3 dimensions, the Lorentz group is SU2, and since it's SU2, there's only one index, alpha, and therefore this is such a term. We can write such a term, and this m is real. So I'll put here, this is complex. A 4-dimensional person would say that this term started its life in 4 dimensions as psi alpha, psi bar alpha dot, with sigma mu alpha alpha dot. So this term started its life as a vector in 4 dimensions. And one thing we'll see a lot in this talk is that if we start in 4 dimensions, we can always try and derive the 3-dimensional theory by compactifying the 4-dimensional theory on a circle. So we start in 4 dimensions, we compactify the theory on a circle, and we derive a 3-dimensional theory. So in 4 dimensions, we cannot add such a term to the Lagrangian. That would violate Lorentz invariance. But if the index here mu is precisely the index that is the circle that we reduce on, this is a scalar in 3 dimensions, and therefore we can add such a term. This term is very interesting. It's interesting because it violates parity. One way to understand that is as follows. Imagine we have a particle, not a field, but a particle. And it's massive, so it sits at a point. We have this notion of the little group, the subgroup of the Lorentz group that still acts on the particle at rest. So the only thing it could do is spin. And therefore, the little group in 3 dimensions is U1. Basically, rotation, if we embed the 2-dimensional space in 3 dimensions, it is as if the spin of the particle is always perpendicular to the plane. In 4 dimensions, positive spin and negative spin are related to each other for massive particles by a Lorentz transformation. Something is rotated this way, I can just turn it around and let it rotate the other way. In 3 dimensions, the only notion of spin is spin along an axis perpendicular to the plane of space. And if we want to change the direction of the spin, we have to rotate it, and it will no longer be orthogonal to the plane. So in 3 dimensions, spin S, which is a number, it's a representation of U1, going to minus S is parity. It's not Lorentz transformation. Lorentz. So in 3 dimensions, changing the sign of the spin is a parity transformation. And in the case of the fermion, it's correlated with the sign of M. So now it's clear why such a term, such a real mass term, violates parity. If we flip the sign of the mass, the particle does not rotate this way, it rotates this way. And these two are related to each other by parity, but not by a Lorentz transformation. I can also do it group theoretically, embedding it in SO4. There's an SO4 transformation that relates one to the other, but from a 3-dimensional perspective, this is parity. What am I doing? So now let's take a theory and couple it. I'm still without supersymmetry. I'm taking such a theory and I'm coupling it to a gauge field. So we'll make it simple. Let's couple it to a U1 gauge field. And this U1 gauge field might be classical or might be quantum mechanical. This is an issue that we'll have to address later when we decide whether we want to do the functional integral over this gauge field or not. But at the moment, let's keep it classical, but it's arbitrary. And we couple it to a fermion. So option 1, we have a fermion with these mass terms, the complex mass terms. But if we have a complex fermion, so psi is a complex fermion, it's complex because it transforms under U1, goes to e to the I alpha psi under the U1 transformations. In 4 dimensions, if we have such a fermion, we cannot give it a Lorentz invariant mass. Because in order to give a mass, we have to multiply psi with psi or psi bar with psi bar. That would violate charge conservation. In 3 dimensions, we can. We can write such a mass term, psi bar. This is this real mass. Again, I remind you, this is this real mass term. So this is a Lorentz invariant mass. We have a 2-dimensional spinor representation. It's complex, transforms under the U1 gauge transformations, and we can give it a mass. So this is something we cannot do in 4 dimensions. Now, since the particle is massive, the right thing to do is integrate it out. This is just evaluating the determinant. There cannot be something simpler than that. We have just one loop diagram of the fermion, but we couple it to a gauge field. So we have diagrams like that when we integrate out the massive fermion. So we're not going to do the calculation, but I'm going to tell you the answer. The answer is I over 8 pi m over m absolute value. Okay, you can think of this as being the sine of m times ADA, which is plus or minus I over 8 pi ADA. So when I integrate out the massive fermion, I induce a Chern-Simons term in the gauge theory, even if it wasn't there before. Now, something is easy to check. I said that flipping the sign of the mass is like performing a parity transformation. Parity flips the sign of the mass. And indeed, it flips the sign of the Chern-Simons term. So at high energies, parity acts by flipping the sign of m. At low energies, parity flips the sign of the Chern-Simons term, and we see that this is consistent. But what's really interesting here is the coefficient. So the fact that you integrate out something that violates parity and you induce something that violates parity, that's not too surprising. But what is interesting here is the coefficient. So I'll have a little aside about coefficient of Chern-Simons terms. On any manifold in 3 dimensions, the Chern-Simons term, if we want the Chern-Simons term to be well defined on every single manifold, the normalization should be 1 over 2 pi ADA. That's on any manifold. If we limit ourselves to spin manifolds with a specific spin structure, the gauge configurations are restricted because we don't have all possible gauge configurations, because we cannot have more complicated situations arising when it's not spin. And if we further pick the spin structure and we allow the answer to depend on the spin structure, then the proper normalization is 1 over 4 pi ADA. Now, in our problem, we have fermions, so we should better limit ourselves to this case. So the Chern-Simons term, properly quantized, must be a multiple of 1 over 4 pi, the coefficient. Otherwise, it's not gauge invariant. But this seems strange because I just told you that we integrated out a fermion, and we got a Chern-Simons term with coefficient 1 over 8 pi. So we did a well-defined calculation, so it seems, and we got a nonsensical answer. So if we started the short distance with the theory as I described it, with a massive fermion, I integrate it out, everything looks right, except that the answer does not make sense. The answer is not gauge invariant. Does anybody know what such a phenomenon is called? Whenever you follow your nodes, you do a calculation, you get something that is not gauge invariant, it's always called an anomaly. That's the rule. So that's called an anomaly. In fact, it's called a parity anomaly. So let me explain that better. What we learned from this computation is that if we start at short distance from the theory with just the gauge fields, no other term, coupled to the fermion, and we integrate out the fermion, we find something that doesn't make sense. So how can we fix that? In order to make the problem really well defined, I know what the logical problem is. That I start with the front blackboard rather than, Unfortunately, it took me 3.5 lectures to figure it out. So fix. No, I've not, but it is. Well, we're already in trouble at one loop. Actually, I did. Sorry, I did, because the gauge field is classical. Since the gauge field is classical, there is no other diagram. Now, if the gauge field is not classical, there could have been corrections here, but the corrections would be proportional to the gauge coupling, and the gauge coupling is dimensionful, and therefore it cannot happen. Yep. This is again one of the characteristics of anomalies, that there's an apparent violation of decoupling. But that's not a confusion. It's not a bug, it's a feature. And in any event, it's not a confusion. This is fully understood. Well, since in the previous lecture you gave the speaker a hard time about being imprecise with the language. So we're going to fix it, because it looks like the way I described the theory doesn't make any sense. Took the theory, just the fermion, we coupled it to A. The A wasn't even dynamical. We integrated it out, and the answer depends on A in a nonsensical way. Fix. Add in the UV. This is called a counter term. And we can do that in two different ways, either with a plus sign or with a minus sign. More generally, we can add it, let me write it like that. We can put here any odd number, positive or negative, multiplying the 8 pi square. So the term with n is just a regular counter term. It respects all the symmetries, it's well defined, we always have an ambiguity in it. The important thing here is that we add, so the 2n part, there's always freedom in that. But what's more interesting is the plus 1. We add something that does not make sense. But this term that does not make sense, the oddness of this number, is exactly cancels the part that does not make sense in the fermions. So if we want to define the theory with a fermion, and I say, oh, we couple it to a gauge field, we have to remember to add this term. Now everything is great, because as we go in the IR, we get this I over 8 pi, the 2n plus 1 that we just copy from here, and then plus m over m absolute value, ADA. And then this is always an even number, so it's a multiple of 1 over 4 pi, and therefore it makes sense. So the lesson is that in order to make sense out of a theory of a single fermion coupled to a gauge field, we must add at short distance a bare, improperly quantized Chern-Simons term. Otherwise, the answer doesn't make sense. Now, what about the mass equals 0? Take this answer and set the mass to 0. Well, everything I said is still true. There's an ambiguity in the sign of this term. It's either plus or minus 1, depending on how we take the limit. But it's still true that we still have to keep this odd, this improperly normalized Chern-Simons term. So what's the lesson here? We start from a theory with a massless fermion. It appears to be parity invariant. I said the sign of the mass breaks parity. So let's set the mass to 0. The theory is parity invariant. But in order to make sense of it, we have to add such a term which always has a non-zero coefficient, which breaks parity. So this is again something which is characteristic with anomalies. Anomaly is a situation where you have a list of properties you would like your theory to have, and there is no way to satisfy all of them, so you have to sacrifice one of them. In this case, the clash is between demanding parity and gauge invariance. Gauge invariance would tell us, if we want gauge invariance, we must add such a term. This was the reasoning so far. If instead we insist on parity, we will say if the theory is massless, let's not add anything. That's fine. The theory is parity invariant, but we cannot couple it to the gauge field because that would not be gauge invariant. So we have two options: preserve the U1 gauge symmetry or preserve parity, and we have to take our choice. Now, if we are really interested in coupling to a gauge field, that's something that we would like to do, would later like to sum over it, would like to couple it to electromagnetism, even if it's weakly coupled, then we have no choice but to add this term, and then we have to sacrifice parity. So this is known as the parity anomaly. Which one? Well, the statement, yeah.
For U1, for SU2 it's familiar.
Yeah, but for U1 it's also true, because you imagine space is S2 times something. Then you could have flux. You could have flux through the S2. In this case, the integral of the dA will give you 1, and then it would look like a particle with which should have properly normalized. So I can actually take, say, S2 times S1, put one monopole flux on the S2, do a gauge transformation that winds around the S1, and derive the quantization. This might not be the most subtle thing, because there might be more elaborate things I could do and get further restrictions that would quantize the system. If you work on R3, then it seems like this thing doesn't need to be quantized. But this is, again, imprecise. It's imprecise because you could still consider Wilson lines and monopole operators, which I'll define soon. And if it's not properly quantized, you will get in trouble there. This is the same thing. In general, you can, if you work on Rn, you think, there is no topology, I don't have to think about it. But some of these monopole operators are defined by removing a point or a line from space-time. By doing that, we induce new topology, because we have new things we could do. We can go around various cycles that are not contractible, because they will have to go through this point we removed. And once we have non-trivial topology, various parameters are quantized.
The more boring kind of math that does this on 3 dimensions uses a...
Well, this one also induces a Maxwell term. I just talked about the leading term at low energies. But, okay, since you asked, let me say, what happens if you turn on the other mass? Well, in order to have the other mass, you have to have twice as many fermions, because otherwise you cannot write it. If you have twice as many fermions, the complex mass does not lead to all that. And now we have two masses we can turn on, two real masses for psi1 and for psi2. And these masses can induce, first of all, there would be a factor of 2, but instead of, say, 1 over 8 pi, it could be either 2 over 8 pi, 0 over 8 pi, or minus 2 over 8 pi, depending on both of them are positive, both of them negative. Or
But when you say it's irrelevant low energy, I mean, there are these fixed points you get.
yes? No, it's irrelevant in the sense that it's a this term is more relevant than the other. At low momentum.
I know what you mean, but that irrelevant. That's saying that low is worth.
I'm doing a free field theory. Eva, this is a free field theory.
Couple it to a gauge field.
Yeah, but gauge field is classical. I'm coupling it to. This is, you see, all these subtlety is a subtlety within free field theory. There are no interactions here. It's one loop exact. It's not that it's one quantity that is one loop exact. Everything here in this theory is one loop exact. It's a theory of a free massive fermion.
If you're talking about the vacuum polarization diagram, and I'm saying that in 3D, 2D leads to higher fixed point.
No, not in this theory. This is a theory that at high energies we have a massive fermion, and at low energies we have nothing. It's a gap theory.
I'm talking about the case that does the four dimensions.
This is sense from 4 dimensions. It's a free fermion in 4 dimensions, reduced on the circle.
I'm talking about the massless limit.
Yeah, same thing. Yeah.
That leads to theories about
No. No. The gauge field is not dynamical. Does not lead to anything exciting. It's a free theory.
How interactions have a diagram there that has interactions between the gauge field and
The gauge field is classical. See, I don't have something like this. This is an external source. I don't have that.
that's fine. You don't need that for this.
Right. So this effect exists even without these terms. There are no there are no.
That's the same with these things I'm talking about, but you should go on. It's a tree level plus one with balance between the tree level beta function and the beta.
There's no beta function here. There's no fixed point here. It's a free field theory. I can make it more complicated and add more fields and add more interactions and it might be fixed points, but that's not the point. This is a free field theory.
You want to keep the gauge field classical?
Let's start this way. I'll soon make it dynamical, but so far it's classical. There will be fixed points, but so far I really want to emphasize that we do not have to add additional elements to understand that. This thing, which is very general, is a property of free field theory.
Yeah, I'm just saying that the Yang-Mills or the Maxwell term is not generally irrelevant when you do.
So what do? We take some gauge field, we specify some classical gauge field, and we do the functional integral over the fermions coupled to this gauge field. And since the fermions are massive, we integrate them out, and the low energy observer sees nothing. And then the low energy observer says, let's vary A a little bit. And as we vary A, the action changes.
For the massive case, it's that on.
But that's also true in the massless case.
Does this term have an interpretation of the 4D theory that you were dissenting?
Yes, but I would rather not get into it. You see, in order to do that, I have to turn on the mass. And this mass is a mass term that is not, you don't usually add in the 4-dimensional theory. It does have an interpretation associated with, again, with anomalies, etc., but I would rather not get into it. I'd like to talk now a little bit about another thing that is new in 3 dimensions that we did not see in 4 dimensions. And for that, I'll talk about supersymmetry, but supersymmetry will play very little role in what I'm saying. We studied the gauge field in 4 dimensions, say f mu nu square in 4 dimensions. So coming from some gauge field A. And now we go to 3D. So A mu splits into 3-dimensional A mu and A4. I'm going to call A4 sigma. In the Lagrangian, in 4 dimensions, we had 1 over G4 square. I'm suppressing coefficients, f mu nu square. And that becomes, in 3 dimensions, 1 over G4 square times the radius. I'm suppressing 2 pi's and so forth, f mu nu square, plus r over G4 square, same thing, d mu sigma square. And now we give it a name. A 3-dimensional person would say that this is 1 over G3 square. This is the gauge coupling as seen by a 3-dimensional observer. So if we take a photon in 4 dimensions, we end up in 3 dimensions with a photon and another scalar sigma. What about the photon? Let's first analyze the photon. The theory of the photon can be dualized to a free scalar field with a kinetic term that has a positive G3 square dA square. Is this familiar, or should I do that? Wow. Okay, thank you. So we talked a lot about duality. This is one of the simplest forms of duality. So I'll do the duality transformation explicitly. So I'll do it here. So we start with 1 over G3 square F mu nu square. So I talked a lot about duality transformations that can actually be done and proven, and duality is the transformations that are conjectured and we don't know how to do explicitly. So this is an example where we do know how to do explicitly. So we start from such a Lagrangian, and now we'll do a set of manipulations that are perfectly valid. First of all, this is a free field theory, so this is something we should be able to do. This F mu nu is d mu a nu minus d nu a mu. But let's give it a name, F mu nu. So we just give it a name. So now it's going to be an independent parameter in the functional integral. But I'm going to add, I'm using Euclidean signature everywhere here. So I'm going to add a Lagrange multiplier. Let's call it A. The mu F mu rho. So what does this Lagrange multiplier do? If we integrate A out, it tells us that F satisfies the Bianchi identity, and therefore it's a properly normalized gauge field. It's a good gauge field. In fact, to really be precise, I have to put here 2 pi so that even the global structure is reproduced properly. But let me suppress the 2 pi's from this moment on. So far I haven't done anything. I gave F a name and added the Lagrange multiplier that forces the fact that it's a field strength. Now I integrate by parts. It's easy to do on the blackboard than in the notes. So I do that. And maybe I flip the sign. That doesn't matter. So now F has no derivatives, and it's just a field with 2 indices. We can integrate it out because we have a Gaussian integral. When we integrate it out with the Gaussian integral, it's a Gaussian integral, this thing is flipped. So we get G3 square dA square. So the lesson of this whole thing is that a gauge field in 3 dimensions is dual to a scalar. In fact, since the gauge theory here is a compact U1, it's U1 rather than R, when we have 2 cycles, we can have monopole flux through the 2 cycle. And in order to satisfy all the quantization conditions, that's why I needed the 2 pi here, but also A should be identified with A plus 2 pi. So A is a compact scalar. So again, this is one of the simplest examples of dualities. A compact scalar in 3 dimensions is the same as a photon in 3 dimensions. This is also one of the simplest examples of an emergent gauge symmetry, because we can run this argument backwards. Start with a compact scalar. It has no gauge symmetry. We run this argument backwards, and we end up with a photon with its gauge symmetry that is emergent. So this was an aside about duality. So now I can rewrite this theory as the dual of this photon, A, plus 1 over G3 square d sigma square. So when we reduce a 4-dimensional photon to 3 dimensions, and again I emphasize this is a free field theory, no interactions, nothing fancy, the photon in 4 dimensions becomes 2 scalars in 3 dimensions. There are 2 scalars in 3 dimensions. In fact, both of them are compact. A is compact, as I explained before, because when I do the duality transformation, I need to ensure that the fluxes of this F are properly quantized. Sigma is also compact, because sigma started its life as a 4-dimensional gauge field. So sigma is identified with sigma plus 1 over r. The only thing that is meaningful about this A4 is the e to the I line integral of A4 around the circle that we compactified. So if we shift A4 by 1 over R, there might be 2 pi's everywhere. If we shift A4 by 1 over R, we don't change the holonomy around the circle. So the upshot is, for this photon becomes 2 compact scalars in 3D. We can trace the polarizations. How many physical degrees of freedom did we have? In 4 dimensions, we had 2, because the photon has either left-handed or right-handed polarizations. In 3 dimensions, we still have 2 degrees of freedom. They are compact. And this whole issue of polarization is not there. So these are scalars. Now, if we are so this has nothing to do with supersymmetry. But if the problem is supersymmetric, we have this vector multiplet in Wesson-Bagger, which includes a photon and a photino. The photino comes down, was a fermion, remains a fermion. But this A and sigma combine into a chiral superfield. So let me try and get the normalization straight. We have something like sigma over G square, G3 square, plus IA. This is a complex field, which is the bottom component of a chiral superfield. So this is a complex scalar. So let's again consider our photon going down to 3 dimensions. We have 2 scalars. Target space is a torus. And we have a moduli space of vacua. Which is T2. So as we go down, start with a photon in 4 dimensions. We don't even need supersymmetry. In 3 dimensions, we have a target space, which is T2. And as we shrink it, it's going to grow because of all these factors of R that we have here. We know it has to grow because a 3-dimensional person, not a person coming from 4 dimensions, if we're just working on R3, then sigma is no longer compact. So on R3, sigma is non-compact. One way to see that, as we said before, that sigma is identified with sigma plus 1 over R. So as R goes to 0, it becomes non-compact. So the target space, we compactify on a circle, is a torus. And if we compactify completely, shrink the circle completely, we have a non-compact sigma and a compact A. Now, if the theory is supersymmetric, the same is true. And we have a moduli space of vacua. And along these vacua, the U1 symmetry is unbroken, because sigma is neutral. And we refer to such a moduli space of vacua as a Coulomb branch. This is terrible terminology here. Because in 3 dimensions, there is no such thing as Coulomb law anyway. Coulomb law grows at infinity. There are no real Coulomb fields in the standard sense. So this is a Coulomb branch of vacua. And it's convenient to make the fact that A is compact, to consider the field X, which is e to the sigma over G3 square plus IA. So now the periodicity of A is well defined and sigma is non-compact. So this complex field X describes the different vacua. There is another interpretation of this X. We can define a new kind of operator. I already alluded to that earlier. This is the 't Hooft operator. 't Hooft did it in 4 dimensions. We'll do that just in 3 dimensions. So we remove a point. So the title is monopole operators. So remove a point from R3 and say that the field strength F normally satisfies the Bianchi identity. So dF is normally 0. But we are going to say that it's no longer 0, but it's 2 pi times three-dimensional delta function at the origin. This is the point we removed. So now, when we consider the space of fields, we do not consider F, which is smooth, which is closed, but we allow such a delta function singularity. Another way of saying it is that we remove the point and specify that the flux on a sphere S2 around it is 1 unit, so 1 unit of flux. We have 1 unit of flux on that thing. So we remove the point, and we postulate that there is 1 unit of flux on that sphere. And now we're going to do the functional integral, or whatever we do, with all the gauge fields with these prescribed boundary conditions. This is an interesting operator to study, and it has interesting correlation functions. In terms of this x, if we dualize A, in terms of A, it is like an insertion e to the IA. So imagine we insert in the functional integral. We're still doing free field theory. So A is a free field. Imagine we insert in the functional integral e to the IA. If we insert e to the IA, then the equation of motion of A, which was originally we had g3 square dA square. Now we have a delta function, so there's an I and a delta function of x at the point where we put the operator times A. This is the Lagrangian with the operator inserted. And if you solve the equation of motion from A for A from here, and you follow through the duality, you will see that it goes back to this equation. So this operator, which has A in the exponent, this operator that has A in the exponent, does this thing. So you can either think of the monopole operator as removing a point from space-time and violating the Bianchi identity at this point. So either remove a point and specify the flux, or do not remove the point and violate the Bianchi identity, or dualize everything and then do something which is very natural, e to the IA. Any questions about this construction of monopole operators? Now imagine the theory is supersymmetric. If the theory is supersymmetric with Susie, I've already said that the natural operator to study is x, which is e to the sigma over g3 square plus IA. So we don't just insert e to the IA. The obvious thing to insert is just x. If we insert x in the functional integral, so we have both e to the IA and also sigma inserted at that point. Then, just as the computation is similar to the computation I did here, I get 1 over g3 square. So what's a Lagrangian for sigma? We have the kinetic term that I just copied. Again, I emphasize, I'm doing free field theory. It's not fancier than that. It's free field theory. This sigma square plus sigma over g3 square with the delta function of x. No I. I really emphasize no I. The solution of the equation of motion of that tells us that sigma behaves like 1 over x, absolute value. So the field sigma, classically, tries to run to infinity near the insertion. Right? We insert an operator. So what A does, we've already discussed. In terms of A, we inserted flux for the gauge field. And in terms of sigma, sigma runs to infinity as we approach this point, because we necessarily inserted sigma together with A. What does it mean in terms of the behavior of the field? Sigma does whatever it wants to do at generic points in space-time. But as we approach the point, sigma runs off to infinity. So the theory really explores this Coulomb branch. So we can put sigma wherever we want. We can put it at 0. We can have boundary conditions that nail it at 0. We can have some interactions that nail it to 0, whatever. Once we insert this operator, it drags sigma to infinity and allows us to explore the Coulomb branch. It allows us to explore this Coulomb branch. And this is precisely the behavior. So this justifies, what have I done here? This justifies something that we saw already in 4 dimensions. In 4 dimensions, in the supersymmetric theory, I quoted the theorem that the moduli space of vacua, coming from solving the D-term equations, is the same as the space of gauge invariant polynomials we can write in the fields, subject to their relations, etc., etc. The same thing is true in 3 dimensions, but in a much more interesting way. In 3 dimensions, the gauge invariant polynomials that we have to consider do not use just the chiral superfields, but we should also include these monopole operators, these operators that look non-local. So we have these operators that look non-local, they're chiral. So we just follow the same rule. We have a moduli space of vacua. The moduli space of vacua is parametrized by some chiral superfields, and these chiral superfields could be either the chiral fields in the Lagrangian or these beasts. So that's something to remember as a new subtlety. I stapled these pages incorrectly and I cannot find anything here. Now let's take this gauge field and couple it to our fermion. So again, the gauge field is coupled to fermion. So what did we do? First we did just free fermion, then we did the free gauge field. Now we try to couple them together, but we are still doing just semi-classical physics. For that matter, we can think of these X's as being classical. So one of the terms in the Lagrangian, and it's good to think of it starting from 4 dimensions, so the Lagrangian has all sorts of terms. One of them is that. We have such a term in 4 dimensions. This term becomes in 3 dimensions psi bar sigma psi. Because that was our rule, A4 becomes sigma. So now we are interested in these regions in field space where sigma is non-zero. This is this Coulomb branch. And you might say that you're not interested in such points in the modular space. You just want to work at the origin. But you still have these operators that will take you there whether you want it or not. Now, what happens if sigma is non-zero? Psi has a real mass. And this is a real mass. So even if psi was originally massless, now it becomes massive. And when we integrate it out, we have an induced Chern-Simons term. We can dress it up further and imagine we have several psis and they have flavor symmetries and so forth, and there are many U1s. We run to infinity, or we run very far in sigma, only with one gauge field. This is the photon that will eventually be dynamical. Such Chern-Simons terms will be induced both for flavor currents and for flavor and gauge. What does it mean? It means that we have, imagine you have A1, and then we have dA2. And dA2 is a dynamical, and so I'll call it an A dynamical. And this is some flavor current. So we induce such terms. We induce Chern-Simons terms for the gauge field that we're going to think of as being dynamical in various flavor U1 currents. Now notice what happens. We had this guy X, which had e to the IA plus sigma. And this operator we said, induces magnetic flux around it. And since it has magnetic flux around it, this guy has a non-trivial expectation value. So we learn that in the effective action, in the presence of this guy, since we have such a term in the effective action, X induces this magnetic charge, And therefore, this X couples to the flavor current. So the upshot of all that is that X has flavor quantum numbers. So we start with a theory with some fermions coupled to one gauge field that we're going to really think of as being dynamical. We couple it to a bunch of, it has a number of global symmetries. Here we use the device coupling them to gauge fields, but we don't have to. So we have, again, a system with U1 gauge symmetry and some fermions and some global symmetry. The operator X necessarily has transformations under the global symmetry. In fact, already yesterday we saw non-trivial mixture between flavor and gauge. The dual gauge group that I described was SUNF minus NC. So what the dual gauge group was depended on what flavor exists in the problem. This is a cousin of the same phenomenon, except that here we can actually see it very explicitly. So we have a monopole operator. That's a, in terms of traditional quantum field theory, this is a local operator. We should consider it as an operator. But now we see that it also transforms under various global symmetries. So this is a new element. This has nothing to do with supersymmetry. In supersymmetry, it becomes only more interesting. So I'll skip some things. So this is what I wanted to do with abelian gauge fields. We can make the, now we can make the gauge fields dynamical, integrate over them, and make Eva happy, because now there will be all sorts of fixed points. It will be very interesting, and I can give a whole lecture about that, but that's not the direction I'm heading. Any questions so far? So far, I've got to say that every single thing I said was a free field theory. No questions. Yes, so I could have added, I could kill it by adding a Bayer-Chern-Simon term, or I could tune the fermions, add more fermions to kill it. So this should be done on a case-by-case basis, but the arithmetic that needs to be done is completely elementary. It all comes from this diagram. With the external lines, we don't even need the gauge field. This is a current. We are looking at this two-point function of the currents. And I already told you what the answer is. This is just 1 over 8 pi. So this is precisely the factor we're not interested in. So what you need to do is what charge appears here and what charge appears here, sum them up, multiply and sum them up. So you don't need to do the Feynman diagram every time. But everything is weighted with the sign of the mass of the particle, right? So you're going to get, so what this diagram will give, so here we'll get Q1, depending on which gauge fields. Here we get Q2, and this will give us the sign of the mass times Q1 times Q2 times various 8 pi's and A and dA and so forth we're not interested in. And now we just have to sum that over all particles. And this will give us this. This would be the coefficient. And we can do it for diagonal Chern-Simons and for off-diagonal, because these are different currents. We could do it for two dynamical gauge fields, two classical gauge fields, classical and quantum, etc. But yeah, this is again something you count on. Once you know what you're doing, you just count on your fingers. There's no complicated calculation. This is not to say that I don't get it wrong.
When the gauge field couples to fermions, there's no problem.
The excellent question. There is no problem. There is a problem. We cannot dualize it. But if we turn on sigma, the fermions are massive. We integrate out the fermions and then we dualize the photon. Right? So that's this. Yeah. So without supersymmetry, in this case, we'll compute loops and these flat directions will be lifted, and that's the end of it. With supersymmetry, loops do not lift it. So it's the same spirit of what I did in my first or second lecture. We go out along the flat direction. Some fields get mass. We integrate them out. In the low energy theory, we have a photon, no charged particles. And since there are no charged particles, I can dualize the photon. But this was an excellent question. Any more questions? No, I cannot. in fact, the Chern-Simons term gives a mass to the photon. And since it gives a mass to the photon, it lifts the flat direction. So you see, it all ties together. I can dualize the photon when I have the flat direction, because then it really makes sense. If I have the Chern-Simons term, I cannot. But there could be all sorts of phenomena, like there is a Chern-Simons term that I put in by hand, another one, so it looks like there's no flat direction. But I try to move in field space. It gives mass to the fermion. I integrate out these fermions. That exactly cancels the Chern-Simons term that I put in by hand. Now I have a flat direction. So when I say dualize and all that, this is in the Chern. This is the flat directions exist after I took into account the one loop contribution from the massive fermions. So let's take an example just to demonstrate it. Imagine we have one U1 with one chiral superfield Q. In 4 dimensions, such a theory is anomalous, so we shouldn't study it, but in 3 dimensions, it's okay. The only remnant of the 4-dimensional anomaly is this parity anomaly we talked about before. So this theory has a parity anomaly. The only way to make sense of it is to add k, which in some terminology, it's a half. This is the terminology that we normalize k with 1 over 4 pi. So we write k over 4 pi a dA. dA. So we add k with a half, or with minus a half. We can put here 3 half also, but let's put a half. Now, imagine we didn't know about all the Chern-Simons term and all that. We are going to have a flat direction with sigma. And if everything would make sense, there would be an A, which is a circle around it. And there is an origin. And the mass of Q is precisely sigma, as I showed before. So if I go to positive sigma, the fermion has positive mass. If I go to negative sigma, the fermion has negative mass. So in here, I have k effective, which is a half, which I had a bare term, say minus a half. And in here, I have k effective equals a half plus a half equals 1. So since I have no, in the end of the day, I have no Chern-Simons term in this half of space, and I do have Chern-Simons term in this half of the moduli space. So what this thing does is to kill this part of the modular space. But here, even though there was a bare Chern-Simons term, the effective one vanishes, and I end up with the modular space of vacuum. I wanted to say a few words about the non-abelian gauge theory, because the fun is always when it's non-abelian, and I'm still in the previous millennium, unfortunately. So consider the SU2 theory. So we have 3 gauge fields and 3 sigmas. We can go along flat directions. So we can let sigma 3, say, be non-zero. But we cannot put all 3 sigmas to 0. Right? We have 3 gauge fields, so I set one of them to 0. So this is a Coulomb branch. For those of you who studied n equals 2 in 4 dimensions, there is a Coulomb branch in 4 dimensions. In n equals 2, here we have a Coulomb branch already in 3 dimensions. Already with n equals 1 in 4 dimensions, which is n equals 2 in 3 dimensions. So we have a Coulomb branch of vacua, and it satisfies sigma 3 is identified with minus sigma 3. That's the Weil group of SU2. In addition, if we compactify in a circle, it's also identified with sigma 3 plus 1 over r. But let's temporarily set r to 0, so we forget that we came from 4 dimensions. So we have a modular space of vacua. We can form our friend X to parameterize it. So what's the physics along the flat directions? Along the flat directions, we have an SU2 gauge theory, spontaneously broken to U1. This is precisely the setup that Polyakov considered in ancient time. SU2 gauge theory spontaneously broken by a field in the adjoint to U1. And in this case, there are monopole configurations. Monopole configurations. Unlike the other monopoles that I described there, the monopoles I described there are things that we put in by hand. The theory does not have such monopole. These ones do exist in the theory. These are excitations. These are smooth configurations of the field. They do exist. And Polyakov wrote a beautiful paper showing that so far we don't even have supersymmetry. We don't need that. And Polyakov showed that these monopoles induce confinement in 3 dimensions. It's a beautiful paper that if you haven't studied, I strongly recommend that you look at. Then Affleck, Harvey, and Witten analyzed exactly the same monopole in the supersymmetric theory. And they showed that this monopole induces a superpotential, which is 1 over x in this notation. So we see here a situation which is very similar to the one I described in my first lecture, except that this is anti-historical order. This was actually one of the motivations for the discussion in 4 dimensions. So what did they show? They showed that an SU2 gauge theory, n equals 2 in 3 dimensions, which is the same counting as n equals 1 in 4 dimensions. There's an SU2 gauge theory. Classically, it has a flat direction. To all orders in perturbation theory, the flat direction is not lifted. But non-perturbatively, we have a potential along sigma that looks like that, thus leaving the theory without a ground state. So I'm not going to do that in detail. But let me make the system now a little bit more interesting. But consider not the 3-dimensional theory, but the 4-dimensional theory on the circle. What's the difference between the 4-dimensional theory and the 3-dimensional theory as far as symmetries? There's only one difference between them as far as global symmetries. The 4-dimensional theory has an axial U1 symmetry, which is anomalous. I emphasized it before. It was an R symmetry. In 3 dimensions, this symmetry is gone. There's another U1R symmetry that comes in, but this symmetry is gone. So if we compactify on a finite circle, the low energy theory should not respect that U1 symmetry. So again, there's an R symmetry. I misspoke before. There is a U1R symmetry classically in 4 dimensions. In 3 dimensions, that U1R symmetry is exact quantum mechanically. But if we compactify the theory on a circle, the fact that there is a finite circle means that the U1R symmetry is violated. So we should take, this term should still be there. So now we do the same theory on the circle, SU2 on R3 times S1 with radius R. And we ask, what's the effective superpotential? So one thing we can have is 1 over x. This is what they found. But we also need something that violates the U1 symmetry, the U1R symmetry. If you go through the quantum numbers, there's only one thing that can exist. This is our friend eta times x. In fact, you could have predicted this term as follows. I said that the theory has the modular space of vacua is subject to such an identification. This identification means that we can invert x goes to 1 over x. There's a factor of eta that I will not be able to get right. It depends. You see, this sigma cube, this sigma 3 is in the exponent, and it's shifted by 1 over r. There's another g square that comes in. Together they give e to the minus 1 over g4 square, which is precisely our friend eta. So I want 1 over x goes to eta x. I'll write it like that. This is an exact symmetry. What does this symmetry mean? It means that if we compactify the theory on a circle, if we do not turn any Wilson line around the circle, A4 is 0, the SU2 is unbroken. Just think of it classically. Imagine we go all the way around and we're doing a 2-pi rotation. If we're doing a 2-pi rotation, that's not the same point because there's no identification, but the symmetry, but the SU2 is still unbroken. So the theory on the circle has an exact discrete symmetry that maps x to 1 over x. Now, what should the superpotential be? For eta going to 0, it should reproduce this answer, this pole. It should be holomorphic, and it should be invariant under this transformation. This is the only thing that it could be. That's actually quite nice, because let's look for the stationary points. To look for the stationary points, we differentiate it with respect to x. So we get minus 1 over x squared plus eta equals 0. So eta is, x is 1 over square root of eta plus or minus. So what do we see? The theory on the circle has two vacua. And as eta goes to 0, which is the same as the three-dimensional limit, they are pushed off to infinity. We should have predicted that without doing any computation. The four-dimensional theory is SU2. It has two vacua. The SU2 theory has two vacua in 4 dimensions. By compactifying the theory on a big circle, this should still be true. The theory on a circle should still have two vacua. The three-dimensional theory, I told you, has no vacuum at all. Where did the vacua go? The only place they could go was to infinity. And this computation demonstrates it. Now, why did I tell you all that? I told you all that because now I'm going to have a real big jump. Because I'm going to ask the following question. Let's take a four-dimensional gauge theory, a much more complicated one, not just the SU2. Take a more complicated four-dimensional gauge theory, which has a dual. So we start with some theory with gauge group G and some matter fields and this and that. And it has a dual field theory with gauge group G tilde and some other matter fields and some interactions and so forth. If we dimensionally reduce these two theories to 3 dimensions, we do not find a dual pair. This shouldn't be surprising. This duality is valid only in the infrared. In the process of going to the infrared and the process of compactifying, these two operations don't commute. In one limit, we just go to very long distance to the infrared, and then we compactify. And in the other limit, we first compactify and then go to the infrared. We might not end up with the same theory. So from the early days of duality, people tried to guess dualities in 3 dimensions, and the first thing to guess is what you had in 4 dimensions, and that fails miserably. Yet people found some examples which are similar that do work. They were mostly motivated by some string considerations. But let's examine it more carefully. If we take these two different theories on a circle, so now I'll be very brief, I'll just outline the reasoning. If we took the naive dimensional reduction, just wrote the same Lagrangian in 3 dimensions, the first thing that would fail would be the symmetries. So the first thing that one should check if you have a dual pair is, do they have the same global symmetries? And that would fail here because this theory had classically 1 U1 symmetry that we threw away because it was anomalous. This theory has some U1 symmetry that we threw away because it was anomalous. But in 3 dimensions, these two symmetries are non-anomalous. They are there, and nothing matches. The quantum numbers don't match, nothing matches. But it's clear what needs to be done just by looking at this example. What we need to do is add to this theory in 4. So imagine we start in 4 dimensions with these theories and compactify on a circle. Compactify on the circle, we'll have whatever we had before, and all we need to do is add here a monopole operator. That will explicitly break the U1 symmetry that we don't want. And on this side, we'll have whatever we had before, and we add eta tilde, x tilde. So now we have another putative duality to check. It's not the naive duality that we had in 4 dimensions. It's the same naive duality, but corrected by adding a monopole operator to the Lagrangian here and adding a monopole operator to the Lagrangian here. Now at least the symmetries match. The surprise is that now everything works. And by now there are many powerful tests of duality, including computing indices. There's a huge industry doing that. And this recipe always works. So this way we can, A, generate tons and tons of new dualities. Second, with one little qualification, all dualities that people guess in 3 dimensions can be derived from this prescription. How much time do I still have?
Well, you're kind of at the end.
Okay, so I'll wrap it up.
Last lecture, yeah, when you
Well, I also started late because there was some...
It's true. You have a few minutes.
Okay, thank you. Thank you. So my original plan was to give you the details of this and to show you how all the dualities work and the symmetries and so forth. But I don't have time, so I'll just wrap it up. First, more locally, this shows the duality that exists in 4 dimensions exists also in 3 dimensions. And there are many examples. It's quite ubiquitous. Second, it shows that we can understand 3-dimensional duality as starting its life as a 4-dimensional duality. In 3 dimensions, we can do that with Chern-Simons terms. So one very, very special case is that something known as level rank duality. This is a phenomenon in Chern-Simons theory, which has long history and very rich subject. It's related to physics in 2 dimensions and in 3 dimensions and so forth. Roughly taking UN gauge theory at level K and relating it to UK level N. So it's a very strange duality. It was one of the first to be found. It actually follows from this reasoning. So the duality in 4 dimensions, if you bring it down carefully to 3 dimensions, namely you add these terms, and then you integrate out stuff, you can derive other dualities, including, for example, this level rank duality. This phenomenon of deriving consequences of field theory in low number of dimensions by studying some property in higher dimensions is very common and very popular these days. A lot of people study the 6-dimensional mysterious theory known as the 2-0 theory. They compactify it on circles and tori and go into 5 dimensions, 4 dimensions, 3 dimensions, arbitrary manifolds, and so forth, and derive properties of the lower dimensional theory that all you need to assume is that this 6-dimensional theory exists. This is in the same spirit. We postulate some duality in 4 dimensions, and we derive many dualities in lower dimensions. So I'd like to really wrap up the whole series of lectures. What did we learn? First, we learned that field theory is still alive and kicking. There are many, many things to do, and it's really interesting. In this case of supersymmetry, the main thing that drives the show is this BPS thing, this holomorphy BPS, chiral topological index. It comes under different names. All of the common thing in all of them, we are interested in objects that are annihilated by some supersymmetries, but not others. I also emphasize, and I would like to emphasize it again, that studying just this, yes, these objects are fun because we can study them, but this is a tiny piece, tiny sliver of what quantum field theory is. And if you match some chiral quantities, this does not yet tell you that you solved the theory, does not yet tell you that you match the 2 theories. So that's an interesting warning sign. So this is the main technical thing. And I think that the main conceptual lesson that we learn is the role of duality, which we see is extremely common in 4 dimensions, 3 dimensions. We can go up and down in dimensions. We can turn on masses and derive different theories and so forth. So I think I'll stop here. Thank you. Oh, that's a very good question. Historically or physically? Historically, yes. N equals 4 duality. The duality of N equals 4 was known before the 2-0 theory was known. And the 2-0 theory gave, in retrospect, the derivation of this duality. Similarly here, we started from duality in 4 dimensions. We derived some dualities in 3 dimensions. You can interpret it 2 different ways. Way number 1, assume the duality in 4 dimensions and derive a duality in 3. Or guess, doesn't matter how the 3-dimensional duality, you perform enough checks to convince yourself that it's right. And then this is a consistency check of the 4-dimensional theory. In fact, I'll make one comment. In the course of doing this thing, some things didn't work. Some examples didn't work. We examined a lot of examples, and some of them didn't work. And then we realized that the bug was actually in 4 dimensions. It wasn't a bug. It was a whole story in 4 dimensions. So this is an example of this thing. There were subtleties that in 4 dimensions were well hidden, but in 3 dimensions, they screamed at you. And which is again something though. When you have a system, analyze it in all possible limits. Compactify it, stretch it, do whatever you can. Because at some limit you might find something will not work. Something that is a tiny effect elsewhere, but becomes a big effect in a different limit. So I'll say one more thing. I'm here till the end of the day, so please come and ask me questions. I don't have to prepare TASI lectures anymore, so I'm completely free.